Remember before the break when we said a lot of rockets were going to launch? Well, a whole lot of them actually did.
And of course, there was a wide range of mission updates and science stories that came out last week as well.
Plus, Beth will be joining us later for an interview with Maggie Thompson about using methane as a biosignature.
All of that and more right here on the Daily Space. I am your host, Dr. Pamela Gay,
And I am your host, Eric Mattis.
and we're here to put science in your brain.
We are on break, so of course all the rockets launched. There were 4 launches in total, 2 from China and 2 from the US. The 2 Chinese launches consisted of a new geostationary communications satellite called ChinaSat 6D and a civilian environmental monitoring satellite called Dahui 1, which will be used to monitor the atmosphere. The 2 American launches were both by SpaceX. As usual, they launched another batch of 53 Starlink satellites. The booster from that launch landed for the 12th time on the drone ship, making it just the second booster to do so. The other SpaceX launch during our break was a West Coast launch of a Falcon 9 from Vandenberg Space Force Base in Southern California that was on just its second flight. It was carrying the NROL 85 mission, a classified payload for the National Reconnaissance Office. NROL 85 was the first NRO mission to launch on a reused Falcon 9, in this case, the booster for the NRO 87 mission only a few months ago. Yes, NRO 85 was launched after NRO 87 because NRO launch numbers are rarely, if ever, in sequential order. As usual for national security missions, no details on the payload were disclosed. The webcast was treated to uninterrupted views from the first stage, showing the almost cloud-free California coast as it returned to the launch site after separating from the second stage. Return to launch site maneuvers to Vandenberg are always exciting because the landing pad is less than 500 meters from the launch pad. SpaceX ended the webcast after the landing, confirming mission success on Twitter later the day. In other SpaceX news, Axiom's AX-1 crew returned to Earth on April 25th after spending 17 days in space, a week more than planned due to weather conditions at the landing zones. As usual, Crew Dragon and Differ undocked the evening before, on the 24th, and the crew spent several hours preparing the capsule for a return. It splashed down in the Atlantic Ocean just off the coast of Florida at 1706 UTC. Unlike the previous Dragon 2 parachute deployments, all 4 parachutes deployed evenly at the same time. The previous odd behavior wasn't a problem, however, just a known side effect of a multi-chute system. At a post-landing press conference, Axiom Director of Flight Operations and Training, Derek Hassman, said the crew was in, quote, great spirits. AX-2, the next private mission to the ISS, is scheduled to fly next spring, having been rescheduled from later this year. The data on Endeavour's performance will be incorporated into the flight readiness review for the next Crew Dragon mission, SpaceX Crew 4. Crew 4 will be a rapid turnaround for SpaceX's mission control, but not the capsule because it is brand new. Crew Dragon Freedom will be the last new-build Crew Dragon, as SpaceX decided it has enough capsules to meet NASA's needs for the rest of the ISS's lifespan. SpaceX will continue to make parts for the Crew Dragons, however, as not everything is able to be refurbished. Crew 4 will carry 3 NASA astronauts and 1 ESA astronaut to the ISS for a 6-month mission. After launching late last year, NASA's Lucy spacecraft to the Jupiter Trojans began to deploy its solar arrays. One of the arrays deployed and latched, but the other got stuck about 95% of the way open, or 345 degrees out of 360. The solar arrays are unfurled using a about 800 centimeter long lanyard or rope system. The lanyard has a prime and a backup motor. According to the team, between 50 and 100 centimeters of the rope are stuck. In early May, the team will use both motors at the same time in a brief tug to hopefully free the remaining rope and latch the solar panel. Ground tests showed that this might be possible. The array is producing 90% of the expected power, which is not a concern for the rest of the mission. What is a concern is the potential for damage to the unlatched array once Lucy starts using its main engine. If this next attempt does not fully latch the solar panel, which engineers think it might not, teams will try again a month later after gathering data. To round out our rocket news, we have an update on everyone's favorite rock puncher. On April 25th, NASA announced that the OSIRIS-REx mission will be extended to visit asteroid Apophis after it delivers its sample from Bennu to Earth next year. The new mission, called OSIRIS-APEX for OSIRIS-Apophis Explorer, will spend 18 months orbiting the asteroid once it's considered a threat to Earth. When it was discovered in 2004, Apophis was predicted to impact the Earth in 2029, causing a disaster. Happily, more data on its orbit has subsequently ruled that out. OSIRIS-APEX will conduct another one of its touch-and-go maneuvers, though not to collect a sample, as there's nothing to return it in. Rather, they do it just to reveal some of the asteroid's subsurface. Coming up next, Pamela will talk about some of the weird and not-so-good science news that came in last week. Stay tuned.
After taking last week off, I am here with a grab bag of news. Some bad, some scary, and some, that's just cool. Let's start with the bad stuff, which, as seems to be true far too often, is news related to our own planet Earth. If you haven't been to Washington State's Olympic Park to see the glaciers, go now. According to a new study in the Journal of Geophysical Research, Earth's Surface, led by Andrew Fountain, the 255 glaciers and perennial snowfields of the Olympic Mountains had half the amount of snow and ice coverage they had in 1900 this year. Since just 1980, 35 glaciers and 16 perennial snowfields have disappeared. To quote the paper's abstract, with warmer summers causing more ice melt and warmer winters causing less snowfall, the glaciers are being hammered in both seasons. End quote. Based on the trends they have studied in those 115 years of historical data, it is expected that by 2070 there will no longer be any glaciers in the Olympic Mountains. Beyond just showing how much we can change our landscape visually, these changes also affect the ability of the flora and fauna of the region to survive. And with no future seasonal glacial runoff, the landscape downstream will change as downstream simply becomes downhill with no more stream. The Pacific Northwest has always been a place of extremes. This stunning temperate rainforest is home to some of the nation's coolest land animals, largest trees, and scariest earthquakes. Back in 1700, on January 26 to be exact, an earthquake between 8.7 and 9.2 magnitudes shook the region that is now northern Washington and southern British Columbia. We know the exact date because of Japan's careful recording of tsunamis. That day, a ghost tsunami, one with no known earthquake, hit Japan. Tsunamis also washed through much of the Cascadia region, destroying numerous villages. Understanding that historic quake is necessary to understand what will happen when that particular fault lets off energy again. Historically, the fault appears to let go roughly every 300 to 600 years. And as I said, the last big quake was in 1700. And by letting go, I mean that fault has earthquakes rated magnitude 8 or higher that will trigger devastating tsunamis. Researchers have studied tree rings, inland salt marshes, and histories of the First Nations people of the region, and pretty much everything else they can get their hands on. And in a new study in the Bulletin of the Seismological Society of America, researchers led by Andrew Kemp document how they have used fossils to study not just the quake of 1700, but also four additional quakes over the past 2,200 years. This evidence came from the layering of fossils in the Salmon River Estuary. At this site, the tsunami in 1700 pushed material 3.4 kilometers inland. This study's researchers obtained 105 core samples from around the estuary and also used data from 114 cores used in a study done in the 1980s and 90s. In these cores, they can both see layers of sand and a variety of microfossils that, together, tell a story of these past quakes. For 1700, the story is simple. 15 meters of slip led to a meter of coastal subsidence. This data was entirely consistent with this fault line being one of the most dangerous in the world. Nothing was found to lessen our reasons to worry. This is your semi periodic reminder that if you live in an earthquake or tornado region, you need to always have an emergency kit in your car and a go bag and emergency kit in your home. We'll have links on our website on how to put one of these together. Stay safe, folks. The world likes to sometimes rock and roll and slip and slide. After that bad news about glaciers and that scary update on Cascadia, I now have a third story that was not led by someone named Andrew. In a new study in PLOS One, researchers led by Rajmi Deekshai demonstrate how bacteria and urea can be mixed with Martian or lunar soil to make bricks. Now, if you're thinking, I don't want to live in a building made of pee and bacteria, I'm with you. But the first settlers on any world are going to have very limited options for building materials. And in the absence of trees to cut down and the energy needed to quarry stone, pea bricks it is? As described in the press release, quote, a slurry is first created by mixing Martian soil with coir gum, a bacterium called Sportscarnia pastori, urea, and nickel chloride. This slurry can be poured into molds of any desired shape, and over a few days, the bacteria convert the urea into crystals of calcium carbonate. These crystals, along with biopolymers secreted by the microbes, act as the cement holding the soil particles together. End quote. While urea is a protein found abundantly in mammal urine, in this case, the researchers obtained the urea from those bacteria. The bricks made so far aren't quite as stomach turning as they could be. I just know, having watched The Martian, that you never know what an astronaut is going to be asked to recycle. All right, that is enough questionable biology for this space science show. Next up, we have some unquestionably awesome astrobiology as Maggie Thompson joins Beth for an interview. Stay tuned.
As we told you about a few weeks ago, a recent study published in Proceedings of the National Academy of Science focused on one particular potential sign of life: methane. In particular, this study sought to list out the circumstances under which biological sources of methane should be considered when it comes to a rocky world. Yes, there are abiogenic sources of methane like volcanoes and hydrothermal vents, but if you combine their presence with the presence of or lack thereof of another gas, you might be able to say that the results are a potential biosignature. And methane breaks down really easily in sunlight, so if you're finding it someplace older and established, there should be a source to find as well. All of this methane speculation mostly came about because we keep detecting methane on Mars, but explanations are, well, light on the ground. Joining me now is Maggie Thompson from the University of California, Santa Cruz. Go banana slugs! To talk about just how we might use methane as a biosignature. Maggie is the lead author on this recent paper, and we're thrilled to have her here today. Thank you for joining us, Maggie, and welcome.
Thank you so much. Yes, happy to talk to you all.
So, you're a graduate student at UC Santa Cruz. How did this research come about? Is this a part of your thesis, or did this happen sort of on the side of what you're working on?
Yes, so this is a part of my thesis. It was a project that got started and was completed all through the pandemic. So I have been working on this project with a postdoc researcher here at Santa Cruz, Dr. Joshua Chrysanthemum Totten, and he originally approached me with the idea for this project. He has thought about method signature quite a bit, and he said we should probably, given that JWST just launched, this is a really exciting time to think about methane biosignatures. And there was a little bit of a rush to try to get a paper out that was an updated, comprehensive review of under what conditions would make atmospheric methane a good biosignature, given that we may be able to detect it in some rocky planet atmospheres with JWST.
Okay, so let's just start with the answer. What is the answer? Under what conditions can we use methane as a biosignature? I mentioned leading in that, you have to kind of look at it with other things. So what are some of
Yes.
those other things that we need to use?
Yes, absolutely. That is a very important point. If you just see methane, that's not just this one smoking gun that you need. You need a lot of other observational clues to really understand how that methane's being produced. So there's several things that we have learned through doing this study, starting sort of most simply. If you see abundant atmospheric methane in a rocky planet's atmosphere, along with significant amounts of carbon dioxide, but very little or no carbon monoxide gas, that's fairly promising. But that alone is also not enough to say, okay, for sure, we know that this is a planet that has life on it. You would also want to be sure that you can rule out all of the different, what we call false positive scenarios. So ways that methane and these other gases could be produced without life first. And it would also be really helpful if you had initial evidence like surface liquid water was a really important thing, as we know, for life on Earth, and some other additional signs of evidence for life would be helpful as well.
So also in my lead-in, I mentioned a couple of those potential false positives, volcanoes, undersea hydrothermal vents. Are there any others that you have to be aware of while you're doing this search?
Yeah, so those are definitely two of the main ones. Another source, and this is most likely only going to be an issue if the planet is relatively young, and that is impact events. So early on in Earth's history, we were bombarded by a lot of, asteroid and comet impacts. Those can potentially produce significant methane, depending on the impacting body. But hopefully we can constrain the age of the system so we can know, okay, is it fairly young? And there's also hopefully some other contextual clues. For example, most impact events would probably produce a lot of hydrogen gas as well. So you would observe that, and that can help you determine that it's probably an abiotic cause of methane.
So how did you guys, what was the method that you used to go about sort of putting this together and get these results and sort of determine what we can use methane for?
Sure. Yeah, that we did a sort of multi-pronged approach for this study. One thing that was really cool and exciting about this is that this whole project could be done just on my laptop. We didn't need any, intense supercomputing power. I was doing a mix of both literature review. There's a lot of literature out there, particularly in the geochemistry and earth science community, looking at things like abiotic methane in hydrothermal systems, deep sea vents or volcanoes. So I was doing a lot of combing through that literature. And then we did some modeling. We did worked on a photochemical model that a graduate student at the University of Washington, Nicholas Wogan, created that was really great and really user-friendly. So we used that to kind of demonstrate how you need a really significant surface flux of methane to be able to sustain it in the atmosphere. Because like you said in the beginning, it gets destroyed by photochemistry very easily.
So when you say surface flux, just for our audience, that's sort of the change of the methane, the up and down of it, correct?
Yeah, it's really just the source, like where you need the methane to be coming out of the surface some way, somehow. And so, yeah, when we say surface flux, I'm just talking about the source that's coming out of the surface.
Did you do any in your literature review, did anything come up about, were you looking at some of the Mars results that have come in where Curiosity's found some methane near the surface and ExoMars has found some as well, but I know there's a whole little controversy about it because the Trace Gas Orbiter didn't find it. So did you look at any of those particular situations?
We did, yes. So I definitely looked at the Mars literature and what various people had been saying. One of the interesting things for our case, where we're looking, even for a planet like Earth today, there's really not that much methane in our atmosphere when you compare it to other things like oxygen and nitrogen. But most of that is still produced by life. And the amounts that they are potentially detecting on Mars are very, very, very small concentrations. Like it's not to the point that we would say it's indicative of life. We think it's probably more likely that there's some sort of surface geochemical process going on that could produce the methane. I mean, of course, we'll hopefully really have a firm answer to that when we get Mars samples back, sometime in, the relatively near future, hopefully. So that will really answer
Hopefully
that.
still in my lifetime, definitely in yours.
I hope so. I know we're all very excited for that. But my thinking is that it's probably probably could be explained by some abiotic process because it's such a small amount.
So what's next in the research for you?
Yeah, so this has been a really exciting project, and there's different ways that we can expand it. One of the things that we looked at in this study was looking at planets that could be analogs similar to Saturn's moon Titan. Titan is the only moon in our solar system that has an atmosphere, and it actually has quite a bit of methane. But Titan's quite cold, so we don't think that life is the source of methane on Titan. It's probably being produced by other outgassing processes connected to Titan's interior. But I think it'd be an interesting case to look at planets that are sort of on that outer edge of the habitable zone. So their habitable zone being typically thought of as where you could have surface liquid water on a planet. It's not too close to its star to get too hot. It's not too far away to be too cold. But looking at that outer edge, planets that might be a little bit on the colder side, but could potentially still be habitable. Would you produce a lot of methane there through abiotic processes or not? And how could you tell if one of those is a biosignature? So I'm kind of excited in the future to look at those potential cases.
So have you or anybody on your team submitted any proposals to JWST yet, or we're still waiting on whether or not that's up and running?
Definitely. Well, so UCSC in our astronomy department has definitely been very active in JWST proposals. So while I personally am not directly involved yet in any of the observations that'll be coming online, I know many others that are, and I know we're all really excited to be able to get some observations, and particularly something like looking at the TRAPPIST-1 system that has a lot of rocky bodies. Just being able to confirm whether or not some of these planets have atmospheres will be really exciting.
Well, it is definitely some exciting work, and I am really thrilled to see graduate students up and coming and working at the forefront of it. So once again, thank you for being here today, Maggie, and we definitely look forward to hearing more from you and your work in the future. So good luck.
Thank you so much. Yes, pleasure talking with you.
This has been The Daily Space. To all of you watching, this conversation ran longer than we can air here on Now Media. You can catch the interview in its entirety on our website, dailyspace.org. While you're there, check out our show notes to find more information on all our stories, including images. As always, we're here thanks to the donations of people like you. If you like our content, please consider joining our Patreon at patreon.com/CosmoQuestX.